过来啦，快点啊！看你都在干嘛？你准备死？楼下的。虽然说503啊。好，快点，快点，好，我们要开始，我们要开始。
Okay, ready?
Yes.
Okay, good morning everyone. Okay, I'm the chair, Gong Yao Lo, come from Tsinghua University. I introduce other jurists.
Good morning, everyone. I'm Wei Jun Li. I'm from National Taipei University. Thank you.
I'm Hu Guang, 里面的 OBE， 他
根据我上面介绍的是可以讲中文，我是台湾大学助理蔡少华，也是跟这个胡老师一样配合的。
大家好，我想要一半中文一半英文National Taiwan University， 那我是蔡主任，那欢迎大家到师大来，那谢谢。
中兴大学是名字。
再补一些说明啊，大家都参加过前面的，昨天有参加比赛了嘛，对不对？规则慢慢熟了，好，然后希望今天的比赛大家能够更进入状况，好，那因为开始之前有些注意事项跟大家讲一下，用中文讲哦，因为昨天曾经出现过那个投影机常常断断续续的，你们换材要先确认无误。用一个动作不小心移一下，看它会断续，因为在有时候偷偷电脑会碰一下会断掉。先做一个它的那个耐力测试，如果不行，要换一台。那接口问题会有一些问题。OK， 好。OK， introduce each team.
Hi, ladies and gentlemen. We are Team Li Ning. I'm the team captain Henry Su, and this is my teammate Jian Liangyu, and my teammate Xu Zixing, and my teammate Wang Jiade, and my opponent Ryan Cai Kui. Thank you.
Next.
Greetings everyone. We are Team Eclair, and I would like to introduce our teammates. This is Senhai, this is Kai-Jin, this is Wu Shen, and this is Hong Hong. And I'm Liu Hongwen.
Hello everyone, we are Team Xiaoxi. I'm the captain of Su, and they are Cai Xinzhang, Wu Junqi, Taiwan, and Ling.
Thank you. Okay. Opponent, challenge the reviewer for the problem.
We would like to challenge problem number 14, falling tower.
So team is enabled.
Oh, I'm so sorry.
No. Accept or not? Oh, I mean.
Sorry.
Then we would like to challenge the reporter for problem 3, swinging sound.
Which thing? Which problem?
Swinging sound cue. Problem 3.
3.
Swinging sound cue.
Set 3. Review and report and review right on your net.切小一点，可以最小，最小，先关掉好了。还有2期，
不是，开始就应该关掉。
关掉，关掉，马上关掉。
I'm the reporter from Texas. Here today I'm going to report problem number 3 showing Sound 2. Sound 2 is a toy consisting of a brigade plastic tube that we can spin around to produce sound. Study the characteristic of the sound produced by such toys and how they are affected by random parameters. And my main focus will be on instructions and the characteristic of the sound and the influence of random parameter response. And here's my outline. In the first part, I'll show my observation videos to compare the tune with curve gate and without curve gate. And I'll show you the experiment equipment I use and the whole setup of my experiment. And I'll get some quantitative explanations in this part. And we'll go on to the modeling of the airflows and the frequency analysis. And the third part will be the sound dependence factors, and which are the length of the tune, the propagation distance, and the angular velocity. And last will be my conclusion. So, in this video, you can see when we spin the tune with curve gates and we spin the tune without curve gates. So, we found that when we spin the tune without curve gate, it won't produce a sound, and we spin the tune with curve gate, it will produce a sound. And we analyzed the sound we record, and we found that when we spin the tune with curve gate, it will produce the obvious frequency here, like this. And if we spin the tune without curve gate, it will only have maybe the motor sound. So we know that the curve gate in this experiment is necessary. And here's my experimental setup. I use the controlling panel to control the motor, and we spin the tune horizontally on the motors, and we use a stick to make sure when we spin the tune, it won't cause deformation on the tune. And we place the microphone in the center of the tune to reduce the Doppler effects. And here's the we put the microphone, we then put the microphone in the center, and we put the microphone in the center, and we found that when we put the microphone in the center, we can reduce Doppler effects, and also the phenomena is more easy for us to record. And so we further transfer the sound we get. So we found that this sound is generated by multiple waves like this, and we change our y-axis from dB to part. So we'll get this chart. So we know that these sounds will mainly influenced by only a few frequencies like this. And according to Bernoulli's predictions, we know that because V equals R omega, so when we spin the tune, the V pumps here will be bigger than here. So the pressure here will be bigger than here. So we know that the airflow direction will be like this. So and we found that we can use the open pipe formula to explain this phenomenon. But this experiment will use the term is corrugations. So we have to fix some factors in this open pipe formula. So we all know that when the airflows are in the center of the tune, the airflow in the center of the tune will be faster. So the pressure here will be smaller. So when the airflow goes through curve gates, it will be like this. And when it hits the angles, and it will cause a vortex here. So we have to change our L to L pumps because L pump will be bigger than L because the distance that the airflow go through will longer than the length of the tune. Also, we have to change our V to Vx pump because the sound velocity in the tune will be affected by the flow velocity. So we pass this to fix these models, to fix this formula. So we'll get like this. So we found that in our experiment, our L pumps will equals the length of the tune plus 10 times radius of the tune, and our airflow velocity in the tune will equals the B omega, and this B is the coefficient that to fix our to let our theory to fix our experiment. And according to reference, we get this formula because we know that the airflow VR, which is VR in the tune, is a range. So the F we get, will be a range, and this F will be the friction, the frequency that produced by the vortex in the tune. And according to Newton's second laws of motions, we'll get this formula, and after calculating, we'll get this one. So the whole series that we're going to get is the VR, which is the flow velocity in the tune. So according to adiabatic process, we'll get P equals this, and also according to continuous equations, we'll get low equals this. So we put this low into this formula, we'll get this two formula. So after calculating these two formula, we'll get the whole formula in our theories. And the V here, is the VR I mentioned before that we're going to get. And according to reference, we get this formula, which is we call the bound frequency in our experiment. And we know that it's a range. And also the open pipe, the tune will have a harmonic. So we found that because this is the range of this frequency, and so this is the harmonic. So if we let the angular velocity become faster, this frequency will increase. So it will be like this. So when this frequency matches this harmonic frequency, the sound will be amplified. And this phenomenon is just like when we play the film will vibrate. And this vibrate will also be a range. So if this range match the harmonic of the tune, the sound of the pipe will be amplified, so we can hear the pipe. We can hear the sound. And here's the sound dependent factors of my experiment, which is the length of the tune, the angular velocity, and the propagation distance. In the first experiment, we control the diameters of the tune is 2.5 centimeters, and our parameters were from 60, 80, 90, and 110 centimeters of the tune. And we found that when we get the same harmonic in different lengths of the tune, when the length is longer, the frequency will become lower. And this also fits our theory. When the L is bigger, the frequency will become smaller. And when we use the same angular velocity to swing the tune with different lengths, we found that when the length is longer, the harmonic we get will become bigger, and also the frequency. It's because V equals R omega, and when R omega is the same, when the length of the tune is longer, the pressure difference, the velocity will become bigger. So the pressure difference between each side of the tune will become bigger. So therefore velocity in the tune will become faster too. So it's easier for it to lead to the next harmonic, and also so the frequency we get will become bigger. Also the harmonic will become bigger. And this is the second experiment. We changed the propagation distance, and which is 0.51 centimeters and 0.58 centimeters. And we let the diameter of the tune is 2.5 centimeters, and the length of the tune is 70 centimeters. And from experiment, we can find that when we use the smaller, when the propagation distance is smaller, it's easier for it to lead to the next step than here. The black points will appear more faster. And it also fits our theory when our propagation distance is smaller. The bumping frequency, as mentioned in my theory, will become bigger. So it's more easier for it to lead to the next step than the longer one. And this is the experiment, the third experiment I do. We change the angular velocity, and we change the different angular velocities from 98 RPMs to 280 RPMs. And we let the length of the tune becomes 100 centimeters, and the diameters of the tune will be 2.5 centimeters. And this is the observation videos that we found that when we spin the tune, it won't cause the sound. And we spin it more faster, it will cause the sound. And we spin more and more faster, the frequency we get will become higher. So we analyzed the sound we get. We found that when we swing the same tune swing the same tune with the same length, and we found that when the angular velocity is faster, the frequency we get will become higher. And this is the result that we get from this experiment. That we found that when we let the angular velocity become faster, the frequency will stepwisely increase like this. And also we can predict the fundamental sound from this chart. We define the fundamental sound will be the frequency difference at here in this angular velocity. And we also can predict when the sound are going to be. When we know that when we get the two frequencies in the same angular velocity, then we know that the sound is going to be like this. We'll get the chart like we'll see two very obvious frequencies here, and we know that the sound is going to be the next step. And why we'll get the two frequencies in the same angular velocity is because I've mentioned that this is the bump frequency I mentioned, and so when the angular velocity becomes faster, it will increase. So we'll amplify when the harmonic of the tune matches the bumping frequency, and the frequency will be amplified. So we get only one frequency like this, that's like this. And when we let the angular velocity become more faster, it will amplify two harmonic of the tune in the same time. So we will get like this. We will know that the sound is going to be, and we'll also get two frequencies in the same angular velocity. And the last will be my conclusion. The phenomenon will happen is because when we rotate the tune, it will cause the pressure difference between each side. Each different side, both sides of the tune, it will have a pressure difference, so the airflow will go through the tune, so the sound will be produced. And we also found that when the bumping frequency matches the harmonic of the tune, and the harmonic will be amplified. And this phenomenon is just like when we play the flute, the vibration of the field is a range, and when this range matches the harmonic of the tune, the sound of the pipe will be amplified. It's just like the phenomenon. And we have 3 parameters in our experiment. The first one is the length of the tune. We found that when we get the same harmonic of the tune, if the length is longer, the frequency will become low. And it also fits our theories when L will become bigger, F we get will become smaller. And when we use the same angular velocity to swing the tune, we found that when L becomes bigger, the frequency will become higher. It's because the V equals R omega. So when the angular velocity becomes faster, when the angular velocity is the same, the length of the tune is faster. So the pressure difference between each side of the tune will become bigger. So airflow velocity in the tune will become faster. So the frequency will become bigger too. And in the propagation distance, we found that when we use the smaller propagation tune to swing, we found that it's easier for it to lead to the next step than the longer one. And the last of the angular velocity, we found that when we let the angular velocity become faster, the frequency will stepwisely increase, and we can predict the fundamental harmonic in our experiment result. And also we can predict when it leaves, and it's because when the bumping frequency matches the 2 harmonic at the same time, which is we'll get 2 frequency in the same angular velocity, and we know that the sound are going to lead. And here's the end of my report. Thank you.
First of all, I'm the opponent of Team Winnie, and first of all, thank you for your hard working towards this presentation and overall experiment. And my first quick question towards your presentation is on page 23. I understand that since the standing wave formula states F equals MB as they write at 2L, right? But can you compare the graph between page 23 and 24? Because both of them are length frequency, length towards frequency chart. But however, I'm just out of curiosity kind of confused why this is an upward trend. However, the chart on page 23 are downward trend. Can you explain that more detailedly?
Okay, because we get the same harmonic, so it only increase the N. So we didn't, and the angular velocity we use will be different, because we are only to get the same harmonic of the tune, and the length of the difference will be cause the harmonic difference. And in this tune, we'll get the same angular velocity. So they were in the different harmonic.
Oh, so they're in different harmonics.
Yes, they are in different harmonics. So we use we only want to get the same harmonic, like maybe N will equals 1, and in different tunes. And how will they be different? And we found that when it's longer, like this, longer here, yes, left to here.
So the chart on page 24 are, let's for instance, the third harmonic, or maybe fourth.
Yes. Because if we spend the tune with same angular velocity, the flow rate velocity in the tune will maybe become different. Like I say, V equals R omega, the pressure difference.
Yeah. So in the chart in 24 is a higher harmonic, right? Is that correct?
We can found that the harmonic we get when the length is longer, the harmonic we go. This chart is also we only want to get the same harmonic.
Thank you.
Opponent takes all.
Can we pause the thing for?
Yeah.
Sorry, because the computer got a little bit stuck. Please say so.
让我暂停。
再 stop 一下。
他没有插，他没有插。
and then connect. Apart. Sorry.
Okay.
No rush.
是不是可以的？那我先拿好。你先跑到第一页。是我现在没有办法动啊，他已经他停了。因为我告诉我
电脑的问题还是电脑的问题？ Sorry.
有没有其他的头？
没有。
那我赶快扣吧。
先不要买，先试看看。可以吗？刚刚说之前要测试一下。
我们测试就可以。
看他们解，先看他们解。先接起来，先接起来。
你先接。
先换一个可以接的再弄。
这台肯定是换3台电。对啊。对啊，这台坏了。
可是这台专用。
对啊，这台是最稳的。还在考虑。没有，这个还在开机。还在开机。
没有，我觉得应该不会是电脑的问题，应该是这个
转接头。
这整接头已经换了。
不是，应该
主线的问题吧。
好，我想。就这台，这个我们看1、2、3、4台，我们这边都是那些。
换哪一条？不是哪一条那个？因为是那个
这一种线，
第上排的线。
那我讲一下。这样子是吗？你要等下用哪一台报告？随便一台，还有吗？
现在接哪一边？现在接哪边？可以吗？
这个已经接，现在
先把它换过来。这台可以吗？
这台的话，
再
那应该。
压到不挡不行吗？
没有，现在就
这台。
而且只要一插上，它就会闪。
那台线是从哪边的？
那一条线是接到这边，但是它送过来的讯号就乱了。
我想直接拔过来，直接插过去好了。
没有，是它过来到这里，有讯号就。
但是这个坏掉了，我觉得是这里切换的问题。对，所以我直接就不要切换了，我直接拉过去。你们这个需要做什么用途吗？这一台？
因为它是跟 review 共用，所以要用这个切换。
但是这一台坏掉。那我觉得每次中插拔，你中间再换好了。
我们可以用同一条线，然后等一下 review 要报告，我们再把线给 review
对对，先把它拔掉。进来先哪一条？从外面的。
可是你这个是 review 的还是？
不，主线从那边过来是哪一条？
应该是这一条。
确定好？因为这样不行。不是，它是切换器问，跟你们都没有关系。
那不是电脑，对啊，那不是电脑。
但这个有人
不用弄，现在拔掉。
那个胶带先死。
直接拉走，不可能我们几个人也都没办法。
对对对。
你跟女朋友都切换好，换人再换，直接贴对。把它过一点，让女朋友别碰到。好，这样子可以了。没有，这样可以，你这样可以，这样可以，等下切换就可以了。再拿一条女朋友本身这里切换就好了。好，不用数太紧。
其实我有 HDMI 接 HDMI 可以直接，那里有 HDMI 可以对接。
你拿一条，我来这里做切换，这里有 HDMI。你去拿一个 HDMI 过来就好，好不好？长一点的，拿来做这里做遥控器切换就好，不要从那边的。对对对。
那台电脑过来，那台档案的电脑，不要把它关起来。没有，那台开键关。
拿过来。
拿过来。
就用我的，我也是 HDMI。
没有，不是，就你是现在打的这个。
剩下哪一条？好，可以的哈。那等一下 HDMI 有一台 HDMI 在这里可以买。好，可以好。多长 HDMI？等一下这台一起让我一起来。现在问题是，有到发现我就把它拔掉了，哎，你有没有一条线，我直接插到那边，2波切换就好了。我从这里做切换，就是我在这里切换，不要去你那边切换了。你有没有这长的线？
刚给刚
给你。
那你这有没有这里的遥控器？
这没有。
也有可能有。
有遥控器。切换起来有没有
？HDMI 的线我请他们回答，因为只有准备。
有没有一条 VG 也可以，他用 VG 跟 HDMI 做切换也可以。
我刚刚给他们的那一条线。
哪一条？
那条。那个
不是。
另外给你们的那一条。
给我。长吗？哦，那太长，不要了。那你接到哪边去？
接到朋友机。
哦，这接到你家，那可以。
这刚好是要拉一下。
对。那可刚好，那就，看一看我们遥控器，找一下遥控器。放下，丢下就好。
我问一下我们遥控器。
我先切看看。好，对，好，那现在就是，1 2，好，你们等一下换，帮忙操作一下，你们的是 HDMI， 你就这样子压这里之后按，对，按这里，对，按这里，然后你关就按到这里，这你们的，按他们就把我上调 ，OK， 好，
谢谢。
我刚确认。
OK， continue。
Honorable jury, fellow competitors, and the most esteemed guests. I'm the opponent from Team Weenie KSHS. I'm Yusuf. Today I'm the opponent of problem 3 Team Sound 2. And this is the problem statement. The problem statement says the phenomenon to produce sound has to be conducted by a corrugated plastic tube. I have to emphasize here. And here are my summary comments of the opponent. First, this is summary. The summary report started with its theory of standing wave formula and vortex. Then the setup has a classic and spinning motor. The parameters of its experiment are the tube length, number of corrugation, and corrugation distance, and omega, which is the angular velocity of the motor. And the experiment results and analysis are FFT analysis. And here are the pros and cons of the reporter. First is the advantage. He has a very clear pronunciation and good animation and mathematical derivation. And disadvantage, he should maybe should organize the variables more detailed. And here are the discussion summary. First question to discuss is in its theory from page 6 to page 7. We see different FFT results and what caused their difference. The second point is why can uncorrugated tube produce a sound? The third point is on page 12. Why would the air jet move upwards when passing nearby the corrugation? And on page 19, can you explain why the bumping frequency can be calculated this way? In page 13, in your mathematical derivation, you can say that in order to let your theory fit the experiment, we can put out our experiment result into our derivation. Would that lose generation? And in problem, in its setup. In page 15, is there any way to quantify the frequency produced by the vortex? In problem revolving experiments, first is how do you change your corrugation distance of your tube? And are there photos of tube with different corrugation distance? And the second question is, if you gradually increase the angular velocity, what do you think will be the relationship between frequency and time? And that's my opponent's statement. First of all, thank you again on working on this presentation. And I would like to continue our previous discussion on page 22 and 24, the explanation of your, you say different harmonic, because I still have a slightly confusion of it. So, in my understanding of the previous discussion that these frequencies here are the same harmonic. And so if you turn to page 24, these should be different harmonics. So as you say here, are the fifth harmonics, right? So on page 23, if you have the same length of tube, however, if this is the lower, is this the lower harmonic or higher harmonic in this experiment, in the chart of page 23?
You mean the number?
Yes. Let me revise my question. In page 24. This is the fifth harmonic, say, if you take tube length 60, for example. But in page 23, the tube length 60 here has frequency of 900, about approximately 980. So is this a lower harmonic or higher harmonic?
In this chart, we only want to compare the difference. So we let the n equals the same.
Yeah. So what I want to know is which n is it?
We just want to compare the difference between each, and we found that it can fit the open pipe formulas. We just want to compare the difference. So we think which n didn't matters because if the n is bigger and the frequency here will become bigger, but the trend will be like the same.
Yeah, I know the intention of your experiment. However, I just out of curiosity and interest that I would like to know the n that you import in this graph. Which because you say these in this chart specifically, the n are the same. And what harmonic exactly is it for this chart? Is it the first harmonic?
Because you mean how do we get this n from?
I mean, as your calculation or your results for these charts, which harmonic are these frequencies in?
I think when we change the n, which the harmonic numbers, the only this frequency will change. And this chart, the mainly focus will be on the difference between the lengths. Yes.
Yes, understand. Thank you. Then my next question will be a bit previous. Can you turn to page 6 and 7? So in this page, you show me that tube without corrugation and with corrugation have a different phenomenon, which with corrugation, obviously, in the problem statement, create a special we can call humming sound. However, a problem I would like to talk later is why does the corrugation doesn't matter. But however, now I want to like to focus on. Can you turn to page 7? Page 5. Sorry. Page 5. The part you show FFT analysis. Sorry, I'm mistaken. Oh yeah, here. So in this graph, you use velocity and get an FFT graph. But you can see through this graph, all of these, you have a very special, you can say, special format or decay of frequency here. How do you compare this graph in page 9 compared with the graph on page 6? Because in this graph, you can see the most distinct frequency here are frequency about approximately 800. But why does the phenomenon in page 9 has a frequency like this? How can you explain the relationship?
Example mentions that when we change the y-axis, it will be like this. And because the value of the sum of like this frequency will be very small, so we think that the mainly focus will be on the sound that is big like this. That is obvious like this.
Okay, pardon me. So, can you? So this is the next chart is the maximized chart of this chart, correct?
You mean this?
Yeah, apart, can you explain that again? Because I'm kind of confused.
Because these frequency they were produced when we are doing the phenomena, because but their volumes of sound will be very small, and we think so that the mainly frequency that generated sounds will be only the few obvious frequency.
Okay, so you don't emphasize on talking about the chart on this.
No, we won't calculate based on the phenomena.
Understand. So can you turn to page 13? Yeah. Here you explain the phenomenon of that when air going through, you can say the dance or corrugation, it goes up. And what does that cause this phenomenon?
Because we know that the air velocity in the middle of the tube will be faster than the side.
Yes.
Yes. So the pressure here will become smaller according to thermal friction. The flow velocity becomes faster, the pressure will become smaller. So when it goes through, that it will be like.
Okay. I understand now. Okay. The next question is, why does the vortex created in the corrugation has to hit, you say here, specific point here, rather than just going down by here, this part? Can I draw?
Yes.
It will be more clear. If I have a corrugation like this, why can't the air flow go like this rather than it has to hit here to create vortex? How can you explain this phenomenon?
We think that the vortex will produce like this, and we think maybe it was have this kind of air flow, but we think the main cause will be will be like this. Yes, I mean.
So you think okay? So you think it doesn't? So you think
because the air field they will because of the pressure difference will go up. So we think that maybe it will go through here, and after it hit the thing also here it will go.
Okay, so later on, after you answer this, later on continue to my next question is how do you quantify or how do you measure the air vortex in this let's say corrugated tube? Because this is your explanation, but how do you get a precise and quantity of the vortex in this tube? How do you yeah?
We can't really measure the vortex here, because but we know that the vortex will cause the frequency that I say the bump frequency, or I mentioned earlier.
Okay, so
yes.
So talking about bump frequency, can you elaborate or shorten the explanation of bump frequency?
Because this will be the flow velocity, and we in our experience the flow velocity we think the tune will be arranged, so the bump frequency will be arranged.
Okay. Okay, understand. So my next question will be around your explanation of your formula here compared to your let's say frequency and length tube results. How can you compare this your equation and explanation to your experiment results.
You mean in the list?
Yes.
You mean the fix of how do
you compare your experiment results with your?
Because we found that in this step the frequency will a little bit change in the same step. So we use the formula the formula to fix this phenomenon.
Okay, I understand. So after our discussion, I want to focus back on the problem statement. So it says it has to be a corrugated tube. Yes. And through your presentation, we all know that corrugated tube causes a vortex. So how do you think? Why is it essential for, let's say, without corrugation? What makes it a distinct difference between tube without corrugation and tube with corrugation?
As I in my theory is that the tube with corrugation it will cause a vortex, and when it has vortex, it will have cause the bump frequency, and when the bump frequency matches the frequency, so we can turn this down. So yes, yes.
Okay, then in one of your parameters you mentioned in your experiment, which is the corrugation length, or you can say D. Can you turn to the page where you talk about D?
This one.
Yes. So how do you verify? How do you change the parameters of? How do you get the parameters of 0.5 centimeters?
We use the same length of tube and also the same diameters, and we will only change we use different kinds of pipe, but only in the same materials. But only the difference will be the corrugation.
So can I like take a brief look at the photo?
No, I don't have the photos. Yes.
Okay. Then my next question will be on because you say angular. Can you turn to page 37? 37. Last page. Sorry. You change different angular velocity, but however, in page 29, I believe, you only show 3 of them in this chart. Why don't you compare all of the experiment results in this chart? However, you just compare 3 of them.
We found that the frequency will become higher when we let the angular velocity faster. And also in this chart, we also changed multiple angular velocity, and we found that the frequency will become higher.
So you just only want to see the trend of higher angular velocity with higher frequency. Is that true?
In this chart, we only want to find the.
Okay. Yes. Thank you.
Okay. Summarize.
Okay. First of all, after a detailed discussion with the reporter, we concluded that with let's say plastic tube, it has to have corrugation to create vortex, and that vortex can let's say easier to create such thing called bump frequency. So that bump frequency, when it meets a certain amount of air velocity, it will amplify a certain frequency. And however, the opponent did not, because of time, he did not explain more detailed relationship on his formula compared to his experimental results. And the opponent would like maybe next time to provide more detailed photo of his experiment to compare.
Okay.
So that.
Now,
Thank you. Thank you, sir.
review.
First, I have a question about both of you. If both of you consider the relative of the sound speed, because we know that the sound speed is relative to air speed. So the sound speed may be the range of the magnitude, not just the
Yes.
Well, as mentioned in my reports that the airflows will influence the sound velocity, so we fixed our formula to fix that.
No, I say that the sound speed is related to the air,
and the tube in the air have the
Yes. Yes. So we have fixed it. Oh, yes.
yeah. I agree with the reporter. Yes, but we haven't actually got into a detailed explanation on this yet. Yeah, I agree with the reporter.
Wait, the relative could be minus or plus, why just plus? Because it may be the different directions are the same direction for the air speed and the sound. Here the tube, the sound speed should be passed through here, and the air flow is one direction.
We think that the microphone position is the same, so we minus. We use the microphone position is the same for the sound to the way of the sound and also the frequency.
But the sound, when the sound goes here, it can go back here again. So your microphone may be able to record that sound.
So we only put the microphone in the center to reduce this phenomenon.
In my opinion, that because the reporter, like we previously discussed, he didn't talk about how the vortex created in the tube. So we can actually not get where the sound is precisely be produced. So it will affect the phenomenon you have.
Next, did you consider the response frequencies for a microphone? Because you know that the microphone has its own natural frequency. So when the microphone detects the spatial frequency, it may be louder than other frequencies.
We don't consider it as in our theories, but we think our microphone is okay for the experiment. Also, our experiment result is based on our theories.
Okay. And next, how big is the range of wind speeds? Because you just have you say that the frequency is the spectrum, not one. So how the range is that? Could you know that?
Okay, start. How?有。等一下再。
Okay, and greetings to everyone. I'm the team from Detail Speaking. I'm a reviewer. And this is our problem statement. And we think that the corrugated plastic tube is important. And third formal state, the spin around is important too. This is our outline. And for overall review to the reporters. First, the parameters are discussed thoroughly in the purpose models and the experiment. And next, experiment results are displayed clearly. And accounts. And numerous theories are spread, not unified. And theory and experiments don't match a lot. And next, about the opponents. Clearly points out of of the pros and cons of the reporters. Ideas are conversion theories and cons. Some questions for discussion is not precise. The first question, the opponent said that why don't encourage to produce a sound? And I think that the reporter's viewpoint is that the encourage tube didn't have the vortex. And in my view, and the airflow inside the non-compression tube is linear. So the report and so and the reporters or the opponents should explain the importance of the vortex or turbulence in sound production. And however, I think that the non-encouraged tube still did win caught sound. Just and next, for the opponent first, why would the airflow from vortex instead of sticking to the wall? And reporters, the pressures above the vortex will be smaller, causing the airflow to flow upward. And my viewpoint is that the pressure is smaller is based on the fact that the vortex has formed. And the reporter shouldn't use the result of the phenomena observed to explain the question. And next, perhaps the sharpness of the corrugation might affect the properties of the airflow. And next is my additional notes and remarks. And the first remark is about how large the range is the frequencies. The frequency for vortex filling, because the reporter said that it is the range, not just one point. And I think that maybe we can use the measures of the sound to that the initial wind speed and the final wind speed and how it decreases how much, and then use the sound speed that because the sound speed is relative to the airflow. So maybe it's at the sound speed plus or minus the airflow can be the wind speed, and that we can calculate the range of the frequencies. And next, about the response frequencies for microphones. I think that it's not quite microphones. Every microphone could have these problems. And in some software like the Laserdisc, it has some tools to neglect this effect. And next question is that why the effect tube is length plus 10R, and why is 10, and why is the radius? Okay, I think that maybe we should use the experiment to prove that the length is correct.
Here will be my concluding remarks. The first will be the reason of sound diffuse is because we rotate the tube will cause the pressure difference. So the airflow will go through the tube and the sound will diffuse. Also, the characteristics in the tube is necessary because it will cause the vortex. So the vortex will cause the frequency. And when this frequency matches the harmonics, the sound will be amplified to frequency. And also the length of the tube with the same harmonic, as I mentioned that the n equal the same, and we also only want to compare the difference between different lengths of the tubes, and also the change will be decreased, while with the increased length. And with the same angular velocity, we found that the frequency will increase with length. And at the angular velocity, we found that the frequency will stepwise increase, and we can predict when the sound are going to be, and we can say what I have said about why in my report, and also we can find the fundamental tones of the frequency of the tune in our result in this experiment. And the last will be the corrugation distance, which the frequency is easier to lead to the next step because the D in our case is smaller, so the bumping frequency will become bigger, so it's easier for you to lead to the next step. And here will be the remarks of the discussions that the harmonic in this discussions that we only want to cause the change difference. So which harmonic isn't the unequals which isn't really important, and the vortex is mainly caused by the angles instead of the fixed off at the term distance. and the bounce frequency is a range. The B is a range, but we can't get the range, but we only know the B is a range, and it can amplify two harmonic at the same time. And the conjugation is needed because the sound production is like this, and also the vortex produced is in every propagations. Okay, thank you.
Any question, Jerry?
First, I have the chance to for the can you tell me why the bump frequency are so broad?
Pardon?
Why the bump frequency are so broad?
So
broad.
Broad. Thank you. I think that because the reporter didn't talk about how big the range is, so I think if he can't quantitate the amount of the range of bound frequency, he maybe can create in his way he maybe can create three frequency if the bound frequency is dominant, because he can amplify three frequency at the same time.
Question for the reporter. Your bump frequency is so broad, but then why is your harmonic frequency are so narrow?
Narrow? You mean the fundamental sense?
Yeah, the fundamental step is not a range. Your bump frequency is a range.
In our experiment, we think that maybe the harmonic frequency will be arranged because the wind velocity in the tune will be arranged, so it will influence the sound velocity in the tune. So the sound velocity will also be arranged. So maybe it will be arranged, but it's very small. Like I showed the graph that is only a little bit difference in the same step.
Just for what's the value of the gamma? You have a gamma in your formula. What's the value of gamma? Yes.
Yes.
What's the value? The numerical value.
This, I think because the air is we can't get the numbers that because the air is it's a fluid, so we can get the.
Depending that turbulence occur, does real number is it real?
You mean the real number in this phenomenon?
So it's a fluid flow.
Yes.
So there's definitely the Reynolds number.
Yes.
And usually we say turbulence is associated, it is related to how small or large real number is.
We only know that in this phenomenon, if the two molecules sound, the narrow numbers will have to be bigger than numbers, but we didn't calculate the exact numbers.
To the opponent, you care so much about turbulence. Do you think?
In my understanding, when the Reynolds number is higher, the chord in the tube should be more complex and more disrupt. Yes.
Well, I just say, is it important to know what the real number is in this case? They didn't mention it, but I just.
I will assume it is important.
How about you?
Okay, first I assume that it is important to because, and in my experiment, I have calculated Reynolds numbers, just estimate about 10,000.
Why is it important?
Because it's about how its turbulence or its linear. And in this model, the vortex is a turbulence model, not linear.
What is fiction of them?
They have to let the airflow can cause no turbulence. The number has that the air can cause less turbulence and there's no number. If the number can that the airflow to cause less turbulence.
Okay.
And I think that.
Okay, Tal. Thank you. Okay.
蔡老师有点，蔡主任，蔡老师，
一般知道，孩子哪知道老人？好，report。for the sun. Report. Show your score. Okay. 7, 8, 8, 8, 9, 8. Okay.
Good job.
Opponent. Ready? 6, 7, 7, 7, 8, 7.
Thank you. Yes.
And the review. Five, 7, 6, 6, 7, 8. Okay, thank you. 10 minutes break. Okay, the opponent challenge the report for the problem.
We would like to challenge conducting that.
9.
Yes, number 10. Rejection. Rejection. Alright. Hey, hold on, hold on.
like to challenge Sweet Mirage, number 5.
Accept.
Fine. Okay, write down your name on the board.
Hello everyone, my name is Ryan Tsai and I'm the reporter from Team Weenie KSHS. I'm back here today to share my research on problem number 5, see mirage with you. So first of all, let's take a look at the problem statement. It tells us that Fata Morgana is a particular form of a mirage, and we can produce a similar effect by shining a laser through a fluid with a refractive index gradient, and we want to investigate this phenomenon. So it mentions the name Fata Morgana, but what exactly is Fata Morgana? And it adds that it is a type of mirage. So what is a mirage? And then it says that by shining a laser through a fluid with a refractive index gradient, we may be able to produce a similar effect. But what is a refractive index gradient? So in order to find out, let's go on to our principles. So first, in order to give you guys a better image, a better picture of what a mirage is, here I show you two actual images of mirages. So first, this puddle-like thing on the road and this inverted image of a ship are both mirages. But the question is that, how does a mirage form? And the key to that is to have a refractive index gradient. So what is a refractive index gradient? If we have one interface formed by two different mediums, one with a smaller refractive index and one with a larger refractive index, now we shine a laser beam onto the interface, and what would happen? It would refract, and more namely, it would bend towards the normal. But what if we have multiple layers of different mediums with this refractive index increasing from top to bottom? Then we know that the light will keep on refracting and bending towards the normal, in the end forming this curved-like trajectory. So we know that what a refractive index gradient can do is to make the light beam curve. And then here are two main types of mirages. First is called inferior mirage, and it is created by a refractive index gradient that increases with the altitude. And next is called a superior mirage, and it is created by a refractive index gradient that decreases with the altitude. All right, with these brief principles, now we can get on to our experiment. So let's do some experiment planning first. We know that we want to shine a laser through a fluid with a refractive index gradient. But the problem, and we expect to see this phenomenon, the light beam curve. But the problem is that how do we create a fluid with a refractive index gradient? So after doing some research, we found out that for circular solution in salt water, there is a really high correlation between its concentration and refractive index. So therefore, we can use this sugar and salt to produce a concentration gradient, which means that we can use this to create a refractive index gradient. So how do we do it? We measure a certain amount of sugar or salt, pour it into our customized acrylic container, and then add water in to let it dissolve from bottom to top. So in the end, this is what we'll get. A fluid that is more concentrated at the bottom and more diluted at the top. Thus forming what we want, a refractive index gradient that is larger at the bottom and smaller at the top. Alright, as for our experiment variables, I included the types of solutions, the days of diffusion, and the inclination, color, and initial height of my laser beams. Now these are my table of samples. I used 7 different days of diffusion to pair up with 5 different inclination angles to pair with 8 different initial heights. And as for my color experiment, I control these variables and change the color red and green as my independent variable. This is an actual image of my experiment setup, and this is the interior. And now we can notice this peculiar instrument over here. What is this? This is actually a handmade multifunction laser beam controller. It has some features listed over here. Here we have this convenient on and off laser switch. And then we also have this angle adjustment wheel. Finally, we cannot miss the hydraulic height controller, which makes our experiment a whole lot more easier and accurate and efficient. Alright, now as for the procedure of my experiment, first I record the trajectory of the laser beam with the camera. So what we'll get is an actual image of the bent laser beams. And the next thing we will do every day we record it is to find the refractive index gradient of the solution each day with a refractometer. So what we'll get is the relationship between the refractive index and the height. So after we get this relationship, we can put it into our Python simulation and get out and receive a simulated light rate. So with this simulated light rate, we can compare this result with our actual experiment results. Now, let's get into our results and discussion. First of all, let's discuss the relationship between the refractive index and height of circular solution. Now from these graphs, we can see that the relationship between the refractive index and the height looks like an exponential curve, and we can double check by looking at their functions. So first, their relationship looks like it's close to an exponential decay. And now if we take an even more closer look, we can actually find out that the exponential curve becomes more and more calm over time. It becomes more smooth and less steep. So to prove this, we can take a look at each graph's decay rate, and we find that indeed it decreases over time. So the exponential curve becomes more and more calm over time. And this actually means that the range of the refractive index gradient widens over time from bottom to top. What does this mean? So at day 1, the range of the refractive index gradient is from 0 to 3 centimeters. But when it goes to day 3, we can see that below 5 centimeters, there are apparent refractive index gradient. And at day 9, the range of the refractive index gradient reaches to 7.5 centimeters. So this can prove that the RI gradient really actually diffuses from bottom to top and widens its range. As for the results for the salt water, they are really similar to that of the circle solution. Their relationship is an exponential decay, and the curves become more and more calm over time. Right, and now let's discuss about the hundreds of pictures that we took and that we recorded the light ray results. So this is a stacked image of the 8 light rays with a 0-degree inclination angle. And at day 1, we can see that 2 laser beams curve. At day 2, 3 laser beams curve, and at day 5, 5 laser beams curve. Finally, at day 11, 6 laser beams curve. So from this, we can know that from bottom to top, more and more laser beams gradually curve. This actually proves what we just said. It is because the range of the refractive index gradient widens over time, causing this phenomenon to happen, making more and more light able to curve. Now we can compare one individual photo with its graph, and we can see that for the 2.2 centimeter light ray, there is an obvious curve, and at 2.2 centimeters, we can see an apparent refractive index gradient over here. But as for the 3.4 centimeter light ray, it remains straight and does not curve. And indeed, at 3.4 centimeters, there is almost no refractive index gradient, which matches our results. Now, the next thing we want to discuss is how a trajectory of one single light ray changes over time. So first, let's take a look at the 4.6 centimeter light ray. At day 5, its y-intercept is in this position. At day 7, it drops a little bit. At day 9, it drops even more. And at day 11, it continues the same trend. So from this, we can actually see that the curvature of the 4.6 centimeter light ray increases over time. It curves more over time. And then, now let's take a look at the bottom light ray, 2.2 centimeters. At day 5, its x-intercept is at this position. At day 7, this position. And at day 9, it moves left, even more leftwards. And at day 11, it continues to move leftwards. So from this, we can actually see that the curvature of the 2.2 centimeter light ray actually decreased. It curved less, and it actually halted its curve. It curved less. So to sum up, the curvature of the upper laser beams becomes clearer over time, and the curvature of the lower laser beams becomes smaller. So it also proves what we said. The refractive index gradient spreads from the bottom to the top, causing this phenomenon. Now, as for the color experiment, we stack these two images together with different colored laser beams. And what we get is that when the initial height is at 1 centimeter, we can see that the red and green laser beams trajectory almost completely overlap one another. And the result is same for 2, 3, 4, 5, and 6 centimeters, which is completely astonishing. So an inference for this is that I think that the laser beams have thickness. So even if there are slight differences in their trajectories, it would be masked by their thickness. And finally, one interesting thing that we found out in our experiment was that even a laser beam with a 0-degree inclination angle can have an obvious curve. So to explain this, we'll have to regard light ray as electromagnetic waves and adopt Huygens principle. And then, provided that we suppose the R gradient isn't continuous. Finally, after introducing our results, we will do some computer software analysis to help prove their adequacy. Now, the first analysis is using image J photo analysis. And the purpose of this is to make sure that the refractive index on the same height is homogeneous. So the way we do this is that we take a stacked image and then split it into many, many horizontal layers. Afterwards, we pick one horizontal layer. And then, so if 3 laser beams passes through the layer, then we can use them to calculate 3 relative RI values. And we can determine whether they are similar or not. And these are our results. We can see that these 3 values are pretty similar. And it's the same for day 7 and day 9. All right, the next analysis we do is the Python 3 simulation. And these are our source code, which I'll just jump faster. All right, and this directly go to our simulation result. So this is the actual image of the -5 inclination angle at day 7. These two, we will simulate these two light rays. So first, the actual x-intercept of the 3.4 centimeter light ray is 23.8 centimeters. And as for the simulation result, it's about 22 centimeters, an error of 1.8 centimeter. And then, as for the 1.0 centimeter light ray, the actual x-intercept is at 10 centimeters. And as for the simulation result, it's about 7.6 centimeters, which is error at 2.4 centimeters. Because I'm worried about time, so I didn't provide more simulation results. And if you are interested, I can show you later. Right. So after doing many simulations, we found out that the error between the simulation result and our experiment, considering the xy intercept, the error are all below 3 centimeters. And here I also listed out 2 assumptions of why these errors may happen. The first is that my measurement of the refractive index wasn't accurate. And second, because the simulation is under ideal conditions, it would be different to real conditions. Finally, I'll use 4 points to sum up my report. So first, the refractive index gradient created by the stir-cross solution and the salt water is close to an exponential decay. And second, we can see that the refractive index gradient of the solution will diffuse from bottom to top gradually, and making the exponential curve more and more calm. Now third, if we change the color, we found out that the red and green laser trajectory are almost completely the same. And finally, we found out that even a laser beam with a 0-degree inclination angle can produce obvious curve. Then these are my future prospects, and thank you.
Question of component.
Alright, so first I would like to ask, could you turn to the page where we're talking about the statement? Basically, in this problem statement, it says that Fata Morgana is the name given to a particular form of mirage. Could you explain what is the difference between Fata Morgana and other different types of mirage?
Sorry, because I made a PowerPoint for that. I can do it right now. It's right here. Sorry.
Alright, because of the time, I will just say. So, Fata Morgana is a type of superior mirage. Is that correct?
Oh, it's a complex type of superior mirage.
Why is it complex? What's the difference between it and some
let me
other?
just show you this PowerPoint.
Okay.
So, yeah, in this scenario, we can see that this is the condition for the superior mirage before, right? Like I just said, the refractive index decreases with the altitude. So there may be one light ray shining this direction, and then here it total reflects. So it reflects into our eyes, and then the next light ray moves in this direction, and so the mirage we'll see looks like this. But what if the light ray goes another route? It may go like this. Let's take a look at the blue line. What if this light ray travels like this and goes into our observer's eyes? Then this may be the mirage that we see. So when we see this really complex and mixed up mirage image formed by more than one mirages, we may call that Fata Morgana.
So I believe that you know what the meaning of Fata Morgana is. So did you observe that in your experiment? The monopole images.
Oh,
or
like
monopole loose pulse delay. Did you see that?
Should I see it? If I want to observe a mirage, that means that I have to take a picture directly in front of the laser beam, right?
Okay.
I tried that, but it closed my eyes and it's very hard to take a picture. Yeah.
So next page. All right. So in the observation section, the reporter mentioned about the problem statement. However, the reporter didn't show us the observation of the phenomenon in the first hand. And in the theory section, the good thing is that the reporter mentioned about the variables and the procedures of the experiments are clear. However, we still think that the theory of this phenomenon is not enough, and the theory cannot accurately predict the experimental result of your experiment. Oops, sorry. And for a setup section, it's really good that you use precise mechanisms to measure to do your measurements. And in the for experiments, the relationship between your variables and are really thoroughly discussed. And however, in the graph inside your experiment results, some are written in Chinese. That's a little and the reason of using Python simulation is a little confusing. So perhaps we could discuss it later. And the lack of theoretical explanations of the experiments. Right. And finally, in the conclusions, it's really good that you combine with simulations to conclude your results. All right. So this is the end of the speech. So now we'd like to discuss some problems. Overall report. Oh, sorry. Anyway, so for a total report, yes, your explanations are really clear. However, the theory that you mentioned at the beginning does not fit really well with your experiment that you have done, and you speak a little too fast. And that's it. All right. For discussion. All right. So the first. All right. So the first question was mentioned in the short question section. So in the first problem, you explain the difference between Baron-Morgana and some other spur mirage. And I want to add some points to it. So do you think that the laser beam have width, and how would it affect the experimental result? The width of the laser beam.
The width of the laser beam, the way it affects our experiment results, for me, it's only the laser color experiment. Because as for the rest of the discussions I made, are all basically how much it curved and the tendency of its curve. Not really, and really less to do with the width of the laser beam.
Well, I think that perhaps the curve of the laser beam is not so related to the problem statement because I believe that the problem statement is probably telling us to focus on the imaging of the mirage. However, I think that the width of the laser beam is an important factor because that if the laser beam is a single line, then there wouldn't be so many different paths. So I believe that the laser beam width could affect the images, the number of images of the Baron-Morgana. That's just a prediction. Anyway, and for the technical problems, as the second problem, I would like to ask, how did you control the initial state of the diffusion system? It means that, it's more about setup. How did you add salt into the water?
Right, so like the image I showed you, I pour salt into the container to make sure that it's flat, and then I add water in. So of course there might be some uneven spots that perhaps we have more salt here and less salt here. But remember, one thing that we did was that we measured the refractive index gradient. Oh, I should show you this picture. Sorry.
All right, so because I believe that this is really important, otherwise there will be some horizontal gradient in refraction index. You must make sure that the gradient happens. There's only vertical gradient. Whereas
so remember one analysis that I did? I used the image J analysis to make sure that the refractive index gradient, the refractive index on the same type is homogeneous. So that's what I want to make sure. That although I may be worried that there are some uneven diffusion, perhaps it diffuses faster, it diffuses slower over here. But in the end, as for the results I found, the refractive index on the same height is close to homogeneous. So I think that I can cancel this concept.
So you prove it through your experiments.
The afterwards analysis, and also I measure the refractive index gradient, refractive index of the same height every day at 3 different spots. So, for example, this is the same height. I measure it here, here, and here. And those numbers, those refractive index values are very, very similar.
Alright, because this is also part of our third question, because I would like to ask, how did you measure the refractive index of different heights?
Sorry, this is also something that I didn't show. Alright, so before I can show you, let me just tell you briefly how I did it. Like I said, I measured the refractive index. Right, like I said, I measured the refractive index of each height every day with a refractometer. So like what I did was using to take some samples from these heights and then measure it with a refractometer. And afterwards, I convert the measured concentration into refractive index. So after I get the refractive index values of different heights, I can import it into decimals and get the fitting curve at last.
Wait, you said you take the could you turn to previous pages? You take samples from those points. How did you do that? Because I think that's really inaccurate. If you use
that is also what I'm worried about. It is inaccurate, but that was the best solution I could come up with. Before we use this method, we considered many other methods, including shining a laser from behind and measure the shift of the angle. But that is very dangerous because I'll need a very, very strong laser, and the measurements of the angle won't be accurate too. And we also thought of using a laser distance measurer to see the time lapse it forms when I shine it and reflect it back to calculate the refractive index of this certain point. But my distance measure later wasn't precise enough.
Alright. I will talk about my suggestion. So in our experience of doing this problem, which we have a theory to describe the refractive index, to describing the relation between the height and the refraction index, and it is called the Fick's law. Have you ever heard of it? Fick's law. The Fick's law of diffusion is a partial differential equation mentioning.
Oh.
Yeah.
I mean you calculate the theoretical value.
Could I use the blackboard to write the terms? So. Right. So according to Fick's law, the diffusion flux is called J, and it is proportional to the concentration gradient. So this is the Fick's first law, and the second law is called trying to tell the concentration at a certain point. The change of the concentration at a certain point due to the time is proportional to.
Oh, actually, I'm sorry. I recall this equation. I researched this before. But there are 2 difficulties if I use this method. One is that this is a 3D model, and if you use this equation to put in our experiment, it won't be accurate. And the next thing is that you see a partial over here. You cannot calculate it with a calculator or a hand. You need to use your computer coding to keep on importing values inside until you get one value that matches your experiment results. There are 2 different ways to.
My suggestion is that if you could really control the initial state of diffusion, that if you could make sure that at the same plane, at each spot, the refraction index is the same. If you could control that, then you can make sure that the refractive index on the same height, and the same height is the same at every spot.
Oh, yes.
And if you control that, then because my fourth question is about why you said that your refraction index and the height is exponentially distributed. Because if you according to this law, the solution to this Fick's law, there's a fundamental solution of this partial differential of this PDE is.
Me using this equation over here, but are you sure that this equation matches with my experiment setup? I only see one dimension over here.
Because the reason why I said that you have to control the refraction index on the same plane is that if you could do that, then you only have to consider one
yes, I did.
dimension.
So I do two double checks. One is that I measured the refractive index at 3 different spots, make sure they're really similar. And the next thing was that I did the image J analysis to make sure that the relative refractive index value at many spots are similar. So
Right.
to prove that
Right.
the refractive index on the same height is homogeneous,
But I think
which
that-
matches your.
But I think the method that you use is a little accurate. So, well, if you could find a better method, and I think that if you have proved that the concentration and the refractive index on the same plane is totally the same, then I think that you could just apply this law to have the correct fitting of your the refractive index. Right. You know what I mean? All right.
I can try in the future. Thank you.
All right. So. Finally, I will talk about again to go back to a problem statement. Is that in your whole experiment, you are basically discussing about the laser beam curve. But this problem is about imaging. So, do you know what the physical meaning of the laser beam curvature?
Physical.
Why are you just trying to measure those curves? Do you know what that means? How would it affect the images that we see?
Like I said, I want to see the tendency of the curve over time. I want to see how it changes. So
Yeah.
that's why I provided many photos of my experimental results, and I stacked the images and I just played them from the first photo to the last photo to show you how the light rays change.
How the light rays change.
And to prove the RI to height relationship.
I think you a little misunderstand my question. I mean that this thing itself, how does that affect the images that we see? The image height. So have you tried to measure the image height using a laser beam?
Oh, I couldn't see an image because if I want to see an image of the laser beam, I would have to take a photo directly in front of the laser.
You
and
mentioned
see
that before.
But so I didn't do that.
So I think
I
that.
tried that, but it's.
And if you, anyway, if you use, if there is from a certain point, and you, if there's 2 light beams emitted from this point, and and this is the observer, I guess I will use the blackboard to explain more clearly. So if there's a certain point right here, and there's 2 light beams going this way, I don't know, and then if the observer is right here, you could. My suggestion is that you could find the function of these 2 light beams and derive it to see where the true spot of the image height is. And you will find the intersection of these 2 laser beams and just make it longer, and you will find image height and the image position.
Yes, but like what you said, all of these you said are mathematical models, and it can be simulated by my computer coding, but it cannot be observed from an actual experiment. In my actual experiment, I also did something. I used this triangular thing and colored it in stripes, and then I put it behind my solution and observe it from here. But I still cannot see an obvious image over here. But what I saw was that, as for its reflection, it has a very, it is very deformed, and we can see that it's very stretched.
Okay. So I will summarize the discussion. So at first I talked about the meaning of fatamorgana with the reporter, and we discussed the difference between fatamorgana and other mirages. And for the following questions, we're basically focusing on the change of refractive index and how we measure it, and how will be better to how to do better fitting the refractive index and the position. And finally, I was trying to explain the we're trying to find a better way to fit the problem statement, because the problem statement is basically talking about the image. So by deriving the laser beam function, and perhaps we could find the correct image height and image position through the derivations and experiments that we've done. Right. That's the end of discussion.
Question of viewer.
So first I want to ask about at your page 61 in your report. Okay, so I will first ask about Poland. What do you think that's caused vulnerable guns to have multiple images?
Multiple images. It's just like we have mentioned in the.
Do you think it's because of the refractive index gradient, or
Of
is
course,
it because of the? So you think it's about the refractive index gradient?
Well, to form a mirage, the refractive index is necessary.
Yeah, I know it's.
And then to form a Fata Morgana where there is many images, I think that the width of the laser beam should also be considered.
I disagree. Okay. And what do you think about is the main focus at why we can observe multiple images?
Sorry.
Why do you think that we can observe multiple images in Fata Morgana?
Oh, like I just said, different light rays that travel through the medium and reaches your eyes.
What do you think that effect is? That gradient, or do you think that is the angle, or something?
It depends on which light ray travels into our eyes.
And in your page, in this page, what is the incident angle of the light rays?
Oh, 0 degrees. It
0
is
degrees.
Stacked image of a 0 degree.
So is your diffusion, your gradient horizontal or vertical?
My vertical.
It's vertical, but if you shot it 0 degrees, it will refract.
Yes. Oh, that's the page I said, but I jumped a little bit.
I don't see that.
I would like to help the reporter to explain this, because that's the reason why I said that the width of the laser beam is really important, because the laser beam has width, so the width is a way.
And about you didn't have any observation pictures that you got, so you cannot prove that your experiments can help us understand what is Fata Morgana, right?
Yes.
Okay, and do you think in your experiments we can observe multiple images?
I tried that, but I didn't see.
So in your theoretical prediction, do you think you can see multiple images?
Under accurate and certain conditions, of course I could. And my simulation, I can just make the line longer, and actually they will meet at the spot where the image should be. But
okay, thank you.
That isn't my actual experiment.
Thank you. And do you think that the reporter's experimental self can help him to see multiple images if he can observe?
I think in theory it should be possible, but
okay. So what do you think that is the gradient profile that we can observe from Fata Morgana? So in that case, yours exponential decay, right?
Yes.
And do you think that other kind of gradients can also help? The other kind of profile can also help to observe.
先给4个。
有接上去了。
哎，接了4个。有。OK。跟老师反映要用遥控器来做事情，遥控器低压就可以，因为遥控选项它是不同的压键换头比这个还好，就不用拿那么多线。OK，Ready？
Yes.
OK，可以了。
Good morning, everyone. I'm a reviewer from Team Excelsior, and today I'm going to present problem number 5, Split Mirage. The problem statement says that phantom Morgana is a name given to a particular form of mirage. A similar effect is reproduced by shining a laser to produce a refractive index gradient and investigate phenomenon. I think the main focus should be why phantom Morgana happens and what is phantom Morgana, how the position of the object of the observer and the changing gradient will affect the phenomenon. And in the reporter's report, he only discussed about the changing gradient and the object's position because he didn't have any observer's view, so there will not be any data about observer's position. But I think that will affect a lot. And this is the reporter's outline. And about the definition of phantom Morgana, he said that phantom Morgana is a mirage. And which didn't fit with the statements. Because phantom Morgana is a kind of superior mirage, and why it's particularly different than other mirages is that it can observe multiple images, not only one, and that affects very much. But he didn't mention that. And in his experiments also cannot provide multiple images, I think. And also, in the theory part, he said about that refractive index gradient can cause the light to bend and make people see mirage. I agree that it can make people see mirage, but the mirage is not phantom Morgana, so that will not fit the problem statement. And it's also too brief to explain the phenomenon, because if you want to explain phantom Morgana, you have to say that why we can see multiple images. And he didn't think that phantom Morgana is specific about seeing multiple images, so that is too brief. And in the experiment part, the reporter did a good job on controlling the variables because he used a lot of mechanic machine to control the variables. But he did that doesn't help explain the phenomenon because there is no observing image, and also the image he will see will not be phantom Morgana. And in the discussion part, he said that what the parameters change the trajectory. The conclusion part, he summarized the results and he gave clear explanation about the conclusion. And the opponent's pros and cons. First, opponents asked about the meaning of phantom Morgana. He didn't ensure about the multiple images either. And also, the measuring of the refractive index and observer mirage is discussed. And the pros of it is that pointing out image of the mirage is important in our experiments. And also, he gave all opinions and straight answers, questions. But he also failed to clarify the phenomenon because he didn't point out that the reporter didn't diss phantom Morgana exactly. So the discussion part today first discussed about the type of mirage. The opponent states that phantom Morgana is the superior mirage. This is correct, but he didn't mention that it has to have multiple images. In the definition, it has to be more than 3. And the reporter agreed. And I think phantom Morgana is a kind of superior mirage requires 3 or more opposite images, which is large refractive index sandwiched between 2 smaller refractive index gradients is required in experiments. So they failed to clarify this point. And also the creation of gradients, they also talk about it. The opponent thinks that it might have horizontal gradients. I agree because the reporters say that it is not very accurate about the diffusion rate about the whole tank. And also the reporter says from experiments it will not affect much. I think the experimental result is inaccurate because when the incidence is 0 degree, the light refracts. But when if the diffusion is only vertical, then it will not refract. So I think the total experimental result with 0 degree incidence angle will not be correct, and it cannot prove the phenomenon. And also with other measurements, this is also measurements of refractive index. So we first talked about how to measure, and he also states that we can use fixed law to assure it. And the report says it's a 3D model, which I do not agree because it's a 2D model, and because it's only diffused vertically. And I think that the measurements the measurement points they both mention is not efficient and not accurate. And there's other point is they didn't say about phantom Morgana's definition, and they didn't talk about different type of refractive index profile.
Okay, thank you.
Thank you.
Okay, report, give a conclusion.
Hello everyone, I'm the reporter from Team Mini, and last but not least, I will make some concluding remarks for this research. So first, the opponent he emphasized many times that I didn't observe the image of the mirage of the phantom Morgana phenomenon, but like I said, I faced many difficulties, and I can do plenty of mathematical models, like you said. I can do plenty of computer simulation, but through my actual experiment, I cannot observe and clear and obvious phantom Morgana phenomenon. So I have to be honest with my experiment results. And then like the reviewer had mentioned, she cannot quite understand why a 0 degree inclination light ray can also occur. But like the photos I showed you, Like the photos I showed you. Like the photos I showed you, these photos, they are all 0 degrees inclination, but there is an obvious curve. Many photos show the same result. So this first, I can prove that this is true and not made up. And also to explain this, I made one page to explain this. Here. And I'll do a more thorough explanation here. So if we regard the light ray as electromagnetic waves, we can consider them as many wave sources. And because we suppose that the reflected index gradient isn't continuous, we can split it into many layers. This is a smaller refractive index, a larger refractive index. Therefore, the wave source will travel faster over here, causing the light ray to bend this direction, which matches our experiment results. And this is according to Huygens principle. So if you actually do the experiment yourself, I'm sure that you will observe the exact same phenomenon.
Okay.
Thank you.
Any questions? Gary?
First, I asked the reviewer. So can you tell me what exactly the condition will produce the what condition, what situation can produce double image?
I think the situation with large gradients and the sandwich between two smaller gradients can help us to form the image, multiple images. Because the light will bend at different various degrees and influence together.
So then the reporter's experiment cannot be.
Yes, so I think the reporter's experiment cannot help us clarify the phenomenon.
Question? Sorry.
This is good point. Do you agree with the reporter's explanation of the 0 degrees laser beam?
No, I do not agree, because if he says that his diffusion is only happens vertically.
Okay, that's okay. How about you?
I think, in fact, I think yes, because
yes,
yeah, because
it's correct.
I think that as just as the reporter shown previously, the laser beam surely curves when the inclination angle is 0. And actually, we could prove that through experiment if you
So in your experiment, I really saw a decay of the reflection index. Yeah, but I think that from both of you, you are disagree with each other because you use exponential decay to describe this phenomenon, and then you use Fields law. And what is the difference, and also why you is correct in your case?
All right. First, the exponential curve that I found out was not mathematical derivation. It was based on my experiment results. It was a fitting curve. The result of the fitting curve was an exponential decay. But as for the opponent, the Fields law, he said that was a theoretical model, which we cannot be sure that it really matches with my actual experiment setup. So
You still insist it cannot be used in your case.
Oh, we cannot be sure because I never tried that before. But perhaps it would work. But one thing that I can be sure is that the exponential curve matches my experiment results.
No, your concentration is planar. Distribution is one plane and then keep changing. There's only one variable.
Oh, but it
So
also diffuses
it's not three-dimensional.
sideways. Will only diffuse sideways, other than because other than vertical.
The index of refraction changes only in one direction.
Yes.
So it's a one-dimensional phenomenon.
Oh, but it's hard to
think about it.
It's hard
for
to
5 seconds.
I understand the professor's point, but one difficulty is that it's hard to control the initial status. I cannot be sure what is the initial conditions before it starts to diffuse upwards. So perhaps this equation needs some fixing.
So maybe the opponent can explain this phenomenon, this equation.
Well, I think that it is sure that it is definitely that the fixed law has to be fixed because the fixed law is actually discussing
Well, I
when.
think our point is,
Yeah.
it doesn't have to be 3-dimensional.
Yeah, we could simplify this problem into a one-dimensional problem because that's the reason.
The question is it valid in this experiment?
What do you say that again?
That you don't have to partial derivatives because it's just one independent variable.
That the reason why the reason why I write it in partial derivative is respecting to the original form of fixed law. But if you just focus on the if you put the time as constant, then it is of course it is only one there's only one variable. The reason why it is related to time is because fixed law is actually discussing about the change in time.
But then,
Your fixed law is missing something. Because according to this, the solution should become uniform.
Solution should be what?
Become uniform instead of a gradient. So do you need something, some term in your fixed law?
You mean that this solution is what?
it's not uniform. It's time dependent, so it takes. Eventually, yes.
Okay.
Confusion law.
Okay. Okay. Thank you. Five, 7, 7, 7, 9, 8. Okay. Opponent. 6, 8, 7, 7, 9, 8. Review. 9, 9, 7, 7, 9. 9. Thank you, everyone. Okay, turn on. Opponent challenges the report for the problem.
Would like to challenge problem number 10.
10,是吧？
Oh, yeah. Sorry, please give us some time to discuss. Sorry.
电脑一。
Wow, we accept the challenge.
10. Write down your name on the board.
sure we have finished our preparation. Alright, so greetings everyone, we're Team Clear, and the problem that we're going to report is the conducting lines. So this is the outline of our report. Let's take a quick view at it. Alright, so let's first move on to our problem statement. So basically, in this problem statement, we have found 2 key points questions. The first question is, how good is the conductance of the graphite pencil line? And second, what are the characteristics that we could investigate? So let's take a look at the observation video. In this video, as you can see, that we're trying to measure the resistance of the pencil line drawn on the paper. And you can see that the resistance of the pencil line drawn on paper is about several hundred kilo ohm. However, the reading is quite unstable. And so these are the 2 facts that we found in this observation video. However, that observation video does not give us enough information, so we should observe some other aspects. So the first experiment that we did is the observational experiment for force, to discussing the force and the resistance. So this is the device that we designed to change the force and the change the force between the pencil and the paper. And this is the result of our experiment. And as you can see, that the force seems to be linear with the log of conductance, but we still have no enough information to explain why this happens. And next, we try to observe the microscopic pictures of the pencil line under the optical microscope. And as you could see that there's a surprising fact that the graphite pieces did not uniformly distributed on the surface of the paper. Instead, it is distributed, and there are many white areas that perhaps are occupied by the paper fiber. And so this picture could determine which model we should use in our experiment and in our theory. Right. So let's talk about this model. Let's talk about this model. The model is called the percolation theory. The percolation theory is basically discussing about when there is a material with many holes in it, and we're trying to evaluate the chance for the fluid to flow through this material. And in the calculations of percolation theory, as the density of the holes gets beyond a certain value, the chance for the fluid the fluid must be able to flow through this material. However, if the density did not exceed this value, then it won't. So this is similar to the structure of the pencil line like this. If we consider the graphite pieces to be the holes and the currents as the fluid, then we could use this model to describe it. And for the case where the fluid volume exceeds, the density of the graphite, when it exceeds the percolation threshold, the conductivity of the material could be described as follows. This is according to the reference that we found. V is the fluid volume, Vc is the percolation threshold, and T is the critical exponent. And for the case that the fluid volume is less than the percolation threshold, according to the theory, it shouldn't be electrically conducting. However, according to the reference and the experiment that we have done, it could. So a possible explanation is due to the dielectric breakdown, where it occurs when the electric field inside a capacitor gets beyond a certain value. And when that happens, the capacitor will transform into a conductor, letting the current to pass through. Alright, so now next I would like to talk about the variables and the experiments that we have done. Since the topic, we are circling around the topic of conductivity. So we're trying to find a factor that affects the conductivity. A crucial factor is the graphite abundance. And there are many ways to change the graphite abundance. For example, the observational experiment that we have done previously is changing the force that could affect the graphite abundance. And another way is to change the pencil ledge that we use in our experiment. But basically, these two, however, these two things we could not measure the true composition ratio of the pencil line. So in our next experiment, we're going to try to make a precise relation between the resistance and the composition ratio of graphite. And in the second experiment, we're trying to investigate some other characteristics according to the second key point questions. So we're also going to measure the IV curves of the pencil line. So this is our first experiment. As you can see, that we're using a DC power source, and we're trying to use a multimeter to measure the resistance of the of the material, and this material is conducting, and we're using the magnetic wire, and the coat is removed to measure the resistance. In our second resistance, we're using a DC power source that we could change the input voltage, and we're trying to measure the IV curve of this material. Alright, so let's see the results. So for our first experiment, we realized that this graph could be separated into 3 phases. The first phase is when the fluid volume is really small, the resistivity of the material is really high, unstable. And when it gets beyond a certain value, the resistivity suddenly decreases. And finally, it will converge to about 10 ohm, and the resistance remains about the same. Alright, so that's the reason why we also find some other references that fit the results of our experiment. In this paper, the author also divided this graph into 3 sections: insulator, the insulating conducting transition, and the conductor. Alright, and so they call the limit between the insulator and insulating conducting transition, the limit between these 2 phases, they call it a percolation threshold. Alright, so we're trying to do what this paper do, and we're imitating its process, and we try to find the percolation threshold of our material, and we realize that there is a dramatic change in resistivity between, it's around 4% when the filler volume is about 4%. And so we determined this to be the percolation threshold. And so this is the result of our, we try to calculate the critical exponent of the formula. So as you can see that since we know that VC is about 4 and we draw this picture again, then we could, according to a correlation, the critical exponent is about 0.99. Alright, so this result could help us explain the reason why this is linear. So if we try to analyze the graphite recording process, then we could realize that using the conservation of momentum, we could realize that the normal force between the pencil, between the polling card and the pencil, the normal force between the pencil and the card is proportional to the graphite mass of the graphite per unit length. Alright, so therefore the normal force could represent graphite abundance in previous discussions. If the this is supposing that the depth of the pencil line is remaining the same. So in that case, then we could substitute the force with the graphite the filler content previously like this, and so we could find that it should be linear and the slope should be the critical exponent if we consider some other factors. Alright, and for a second experiment of the second result, the result of the second experiment, we use 5 different types of pencil and measure the pencil line drawn with each pencil, and we try to measure the IV curve of each pencil, and we separate it into 2 groups: the softer pencils 6B, 4B, 2B, and harder pencils F and 2H. And this is the control group, which we also measure the color code resistor found in our laboratory, and we measure its IV curve, and we realize that it fits the Ohm's law. And using the same device, we measure the softer pencils, and we realize that it is really nonlinear. The IV curve is really nonlinear. Right. And however, if we compare the softer group to the harder group, it is surprising that the softer group is more nonlinear than the harder groups. And so the reason why we separate these two groups in this way because that the magnitude order of resistance is different. Right. So we try to explain the difference in the linear properties here. We mentioned that in this picture there are many white areas which is occupied by the dielectric, not graphite. And so we believe that the dielectric breakdown could happen as we increase the voltage. So as we increase this voltage, the gap between these graphite pieces might break down and lead to the currents lead to the increase in current. And an interesting phenomenon that we observe is that when we increase the voltage, beyond about 30 volts, and in the case of 6B pencil, the current on the motor repeater keep rising, and it doesn't stop, and in the end, the current suddenly disappeared, and when we reveal the device, the conducting line has burned out. Alright. So we try to find the reason why it burned out, and we realized that we searched for some reference, and we realized that the breakdown, the form of breakdown in solid substances is called partial discharge, and the heat created would carry through a channel in the dielectric and conduct current through the gap. And so the process of carrying through a channel is similar to the phenomenon observed in the sulfur group, where the conducting line burned down finally. Alright, so now conclusions. So according to the previous discussions, we realized that the pencil line could be discussed in two different cases. The first case is when the filler volume exceeds the percolation threshold. In this case, the conductance of the graphite pencil line could be represented by the following formula that's mentioned in previously, and the value of T could be measured through experiments. And for the case of when the filler volume does not exceed the percolation threshold, in this case, the current could still get through the material through breakdown, so the conductance wouldn't certainly approach zero, but would be much lower than the case higher than percolation threshold. And so to add a point that the reason why the softer pencils have more, the IB curve is more nonlinear is because that the gaps are smaller, so the breakdown effect would be more effective. Alright, so this is our conclusion. So this is the end of our report. Thanks for listening.
Okay. Opponent.
And thanks for the reporter for his presentation. And can we please turn to page 4?
Anyone to help you? Alright, 4.
You mentioned that the experimental result you have observed is unstable. Can you further explain why?
Well, because that in this experiment we use our hands to operate the needles. So this is one reason. And the second reason is perhaps, basically, I believe that the human error,
And what is the digital millimeter measuring during the video?
What did you say?
What is the apparatus measuring in this video?
The apparatus?
Yes.
Oh, you mean this millimeter?
Yeah. And what is it measuring? Is the resistance?
Resistance.
Okay, thank you. Can you please turn to page 8?
This.
And what is this page about? Is it the theory about the electron hole?
Well, we can discuss it later. Oh, sorry, that is sorry, not. I thought the time is up. Anyway, this is the case when the density. In this case, we think that the structure of the pencil line is similar to the percolation model. So we're trying to demonstrate that when the density of the graphite pieces exceeds the percolation threshold, according to the reference that we found, the conductivity could be expressed as this formula.
Do you think the pencil conductor is a conductor or a semiconductor?
You mean the pencil is a semiconductor or graphite, right?
In your opinion, what do you think the pencil conductor is?
It is a semiconductor actually, but it is a little complicated. The characteristics.
Okay, thank you. Cells here, so I'm going to the problem number 10, production lines. And the problem statement was basically about a line drawn with pencil on paper can be electrically conducting, and to investigate the characteristics of a conducting line. And the main focus what I investigated was the pencil line are conductive and the reason causing the characteristic to change. And to solve this problem, the opponent believed that we have to identify the reason for it to be electrically conductive, which is because the composition of pencil and the structure of graphite. And then we have to understand the differences of the characteristic of the line, including temperature coefficient, conductivity, and electrical resistance. And finally, we have to investigate conductivity under different circumstances, including the different structure and surface of paper, and the temperature change, cross-sectional area, and the ratio of graphite. For the strong and weak point of the reporter, first of all, he had explained physics meaning of the equation clearly explained, but he did not explain the deviation and between the theory and the experimental data. He did an explanation on the theoretical derivation, but he also did not explain about the theory limit of his theory. And he showed about the experimental setup of his experimental result, which is the car, but he did not mention about the reproducibility about his experiments. And for the following stage, the opponent would like to discuss on a few points. First of all, the opponent wants to discuss on the data analysis, which is about the characteristic of the line. And the report did not mention about the temperature coefficient, resistance, and whether if it is an ohmic conductor. And he also wonders about the resistance magnitude of the parameters that the reporter has discussed. And for arrow, due to the rough surface of the pencil structure and the unevenly contained structure in pencil should also be discussed. And finally will be the accuracy, which is about the voltage and current, and the reporter also did not mention. For the theory assumption, the opponent wants to discuss on whether the theory fit the experimental result of the experiment he has done. And the theory limit, as I have mentioned, that the reporter did not mention. And he also wonders about the parameters considered in the report and the characteristics that should also be listed in the theory assumption. And for the setup, first of all, the opponent wants to ask about how does the reporter measure the resistance and other parameters, and how to quantify the carbon capacity. And finally is how to draw the line and how they conduct the pencil line with the apparatus they measure. And finally will be the parameters. The reporter does not mention lots of parameters, but the opponent believes that there are some important parameters such as the length and the thickness and the ratio of graphite of the pencil conductor. And also the environment around in the measuring situation, including the temperature, paper friction that will further affect the adhesion of the paper. And finally, the opponent also believes that the DC and AC of power should also be considered and discussed. I would like to skip to the next phase. Once again, thanks the reporter for his report, but can you please turn to page 13? The opponent wonders about the access of V percentage. The opponent, can you further explain what is the access about?
Well, in this experiment, we manufacture the pencil by ourselves using we use clay and graphite powder to manufacture a pencil, graphite composite by ourselves. And the V% is actually the volume percentage, of the graphite powder.
Of what?
Of the graphite. And if we consider the density.
The graphite ratio? Is that a graphite ratio?
Yeah, graphite ratio.
Can you turn to page 12?
Yes. This is another experiment.
The experimental setup of the previous experiment.
This?
Yes. And is that area the pencil you have made?
I think that the picture is not clear, but no, this is not. These are not. There is a this is a quarter composite, but it is not clear in the picture.
The
But
problem
well, this is the
mentioned that you have to draw a pencil line on paper, but it seems like your experiment result does not fit the problem statement.
no, yes, in our observational experiment, we did draw the pencil on paper, and we also explain we also explain in our explanation. We explain the case when we use different force to write on pencils. So yes, we discussed the case of the pencil writing on paper. But in this experiment, we were trying to use another way to measure the graphite ratio of the composite.
Okay, thank you. Can you please turn to page 19?
19.
Yes, you seem to use another way to change the content of graphite. Do you agree?
Content of graphite.
Yes, content of graphite.
The content.
Content. Yes.
Content. Yeah.
And
But
you mentioned that the softer pencil is the 6B to 2B. Is that true?
Well, in our definitions, that's true. We're just trying to. The reason why we separate these two groups is because the magnitude order is too different, and we place it in a same graph.
So why is the 6B to 2B the softer group instead of the 8th and the 2H?
All right. Perhaps that is not an accurate usage. Perhaps we could call it a flatter group or something else. But I know that 2B, 6B.
Okay, thank you. The opponent believes that the 6B to 2B is more hard since that the more graphite is contained. And can you please turn to page 19?
19.
And in this page, in your report, you have mentioned that you use the Ohm's law.
We're trying to examine whether the pencil line follows the Ohm's law.
So you use the Ohm's law.
We're trying to examine, but if you say use it, well, not so. Not quite.
So if you include the Ohm's law in your experiment, have you ensured that the pencil conductor is the ohmic conductor?
According to this experiment, as we could see that the IB curve is nonlinear, so we think that the pencil line, if we just see the pencil line on paper, it's not an ohmic conductor.
If it is not an ohmic conductor, how can you use Ohm's law in your experiment?
Well, we are trying to see if the graphite pencil fits the Ohm's law. So we're measuring the IB curve.
So after observation, it does not fit.
Yes. Yes. So from that is the conclusion of this experiment. We see that the pencil lines on the paper is not an ohmic conductor. This is the reason.
So you only use the parameters of the hardness of the pencil to clarify whether it is an ohmic conductor.
No, I mean that this is also not a ohmic conductor actually. If you could see that there is still slight error of it, but I think that we believe that the softer pencils and hard pencils, their conducting mechanism is a little different. So
okay, thank you.
Yeah.
The opponent believes that the pencil conductor fits the ohmic conductor, and it is able to have proportional relationship between the voltage and the current. And can you please turn to page 10?
Okay.
Seems like the page of the parameters that you have measured.
Yes.
And have you measured the length of the line between the other parameters?
The length of the line.
Yes.
Length.
Oh, how long is the pencil line?
Length.
Yes.
I see.
How long is the pencil line?
Well, I think that the length of the pencil line is not the crucial point, but the length that we use to measure the pencil line is important. Yes, we measured it, but we fixed it. So.
And what do you see the relation between the length and the resistance?
Oh well, I think I forget it. Well, before in the long time ago, we used in our observational experiment. In fact, we have done another observational experiment to see if the where is it? In this experiment we used the same force and we draw a line which is about 5 to 6 centimeters, and we divide that pencil line into 18 different sections.
And what is the relation between the length and the resistance?
And in this case, the length and resistance is proportional. but
it's proportional.
But I believe that the part that it doesn't, you said that the reason why the pencil line follows the Ohm's law is because that the length is proportional.
Okay, so the opponent agrees with the reporter. And in this picture, it seems that he used a car to draw the line.
Yes, because we use a car because we want to neglect the resistance, the friction between this surface.
And what is the maximum mass of, what is the maximum force of the downward pressure?
Downward pressure? Well, why is it not working? So in this experiment, the biggest force that we use is about 400
And do you think there's any limit in this experiment?
Well, we aren't able to reach that limit because if we use harder, and if we use bigger force, the paper will be penetrated.
When the force is too large, the force may scratch the graphite structure and destroy it. Do you agree?
Yes, but we aren't able to reach that limit because our paper penetrated first.
The opponent believes that graphite structure is breakable, and
yes.
if the force is too large, and the graphite structure will be destroyed, and it will be no longer conductive.
Yes, I believe that is right.
Okay, thank you. Can you please turn to page 21?
Just which page?
21. You have mentioned that the line was burned.
Yes.
So,
when we apply.
So does that mean that when you're doing an experiment, there's a significant temperature change?
Yes.
And do you know the temperature coefficient of the conductor?
We're not sure about that, but we believe that that is another factor that we should examine.
Yes, and it will affect the experiment result quickly. So do you consider?
I believe well, in this experiment we didn't consider, but I think that is another.
And it seems like your experiment result have a little deviation between your theory, and is this the reason why?
What?
Seems that your experiment result have little deviation between the theory, and is the reason of temperature coefficient not considered?
Well, I believe that during the breakdown process, there are many heat that was created during this process. So yes, the heat is an important factor during the conduction
Okay,
process.
thank you. The opponents believe that the temperature should be considered, and it will affect the experiment result greatly. And since you did not consider the temperature, and what do you think that the temperature will affect the experiment results?
Well, and interestingly, I believe that the rise in temperature would decrease the resistance. This is interesting.
Will decrease the resistance.
Because as you can see that when we in this graph, when we increase the input voltage, when it exceeds a certain value, the current keep rising and didn't stop. And so this process tells us that the resistance.
Okay, thank you. Can you please take page 11?
Yeah.
And in your experiment setup, you only use DC power supply as your part in your experiment. And have you measured the AC?
No.
No.
No. I believe that might affect the result too, but we didn't consider it in this experiment.
The opponent believes that the AC will affect the experiment results, and the reporter should consider in his experiments.
Alright.
And finally, and can you turn to page 8 again?
8?
Yes.
What's up?
8.
Yes.
Can you explain again that why do you think that the pencil conductor is a semiconductor?
A semiconductor.
Okay, thank you.
What time's up?
And in the discussion we have made, that we have discussed about the data analysis, about the temperature coefficient, and whether it is an ohmic conductor. Since that the reporter did not really mention about the Ohm's law in his experiment, so it is not important, but the opponents still believe that the pencil conductor is an ohmic conductor. And for the temperature coefficient, the reporter did not discuss about the temperature, and he has mentioned that the pencil line have burned, which means that there is a significant temperature change. And for the theory assumption, the reporter has lack of theory and lack of theory fitting and the connection between the theory and the experiment result. And he also did not explain the deviation between the theory and the results. And finally, the setup, he did not draw the line on paper as the problem statement has mentioned. He used the graphite contained to make it. So it does not fit to it. And the recorder also have lack of parameters, so they should be fixed. Thank you.
Okay. Review. Question or review.
So here are few questions for both opponent and reporter. The first one is for reporter here. How do you control forces on the paper, since you just mentioned the
Oh, well, I didn't explain it properly. Sorry. So in this experiment, we raise this lifter and make it make the paper contact with the pencil, and we look at the panel of the
okay,
scale to control them.
And for the pencil, and what is the real mechanic behind the car?
The car?
Yes.
You mean that the model of graphite?
Yes, yes.
Graphite reporting?
Yes.
We have mentioned in our report here. But so in this model we suppose that you mean, do I need to explain this whole model?
Okay, no, thank you. And another question is that after drawing once and once again, the top of the paint and the pencil will become blue. Is that correct?
Yes.
So how can you solve this problem? And since it's a kind of around.
Well, every time we finish an experiment, we will sharpen the pencil again to make sure that the pencil line is remaining the same. And we'll also measure the width of the pencil line drawn on the paper.
And so for the opponent, you have. And so for the opponent, you have mentioned that the temperature will affect the phenomenon of this experiment. Can you explain that more detail?
Again, according to the law of temperature coefficient, there are actually a specific relation between the temperature and the resistance. And the opponent believed that when the temperature increased, the conductivity would decrease.
Okay, and for the report, can you please turn to page 8? And you have mentioned that your actual experiment meet the percolation threshold.
Yes.
And how do you make sure that?
In our first experiment, take the first experiment for example, we realized when there is a dramatic rise in resistance, we believe that the change in between these two states is the percolation threshold.
And okay, so can you turn to the microscope?
Microscopic picture.
Yes. And you have mentioned that through the microscope you observe that the graphite isn't distributed evenly. How do you fix this?
Fix this?
Yes.
Well,
yes.
this.
对，如果是我那个文件的话，会比较一定都会在外头。就是出现右转到外头，就是那个方向，做到时间会稍微快一点这样。那如果到我想的话，会先绕回来这样子。
所以我应该没有到你再走到外头拍下去再做这个。
对，可以做一下。
so again, I would like to thank the presentation for both opponent and reporter, and this is the reviewer of conducted mind. This is the problem statement they have already mentioned. And let's first quickly look at the summary and comment of the report. The phenomenon they mentioned is that the line drawn by a pencil and can conduct electricity. And the laws applied to is a definition of conductivity. However, I lose of time, so actually there's a questions I'm gonna discuss with the reporter. How does he define the conductivity? And they still use resistance. And so for the changing factor, they use the length of line, normal force, and input voltage. And for the setup, they use pencil holder, paper, and microscope. And here is the pros and cons for reporter. And they did many researches, and they did discuss deeply into the mechanism of the conductive line. However, there's some suggestions for them. They should clarify the variables which means that the independent and the dependent, which of the parameters are controlled or not. And there are many variables that are hard to control in this experiment, including the sharpness of the pencil tip, constant number of folds, and graphite distribution. So we suggest that the reporter should give us more picture or descriptions, and thus we are able to understand more. And so here is the summary and comment of the opponent. And the pros and cons is as follows. They have excellent questions, clarify many points, and focus on, sorry, this is just a mistake. And therefore, the suggestions that they should be more, put more discussion on the theory would be desired, since they are only focused on the experiment, and they seem to take it forward to the wrong session and focus on the more reported work. And here is a summary and discussion for. First, the first question is that the opponent asks, do you think that the pencil is a conductor or a semiconductor? And the reporter answered, it should be a semiconductor, but it's complicated. And as a view of a review, we think that from our chemistry knowledge, pure graphic isn't a semiconductor. But there is a possibility that since the pencil lead which is a mixture, can show semiconductor characteristics. And so the second question is, how do you control the proportion of the graphite and clay in a pencil lead? And we are it's amazing that they manufacture the pencil lead. But as I just mentioned, they didn't clarify it very detailed, so we still have many questions toward this. And so how can they make sure that the graphite and clay powder are mixtured evenly as a mixture? And so here, do you think pencil lead is an ohmic conductor? And the reporter respond that no, according to the experiment results. Okay, and so the fourth question is that if you use pure graphite, do you think that it would be an ohmic conductor? And for the answer for reporter is yes. From our results of the 2H and F, they are close to pure graphite, and we can see that they present characteristics close to an ohmic conductor. But for reviewers' opinions, we cannot be sure of that, and since we anticipate the reporter to do an experiment of that and take the note of that too. And so here's a question of mine. The first question is, how do you know when your actual experiments meet the pre-correlation theorem? Since when during the presentation of reporter, they didn't mention that very detailed, so I'm able to understand that. And through a microscope, you observe that the graphite isn't distributed evenly, and actually the reporter only mentioned this point, but they didn't give a solution over this. And so after a pencil, draw many lines and points would become dual. How do you control this variable? And so what is so a solution is desired. And how to control the normal folds and the pencil excessive paper. And so,
okay.
So thank you.
Reporter give a conclusion.
Alright, so and in the discussion, the opponent asked why. The discussion asked why the percolation model has to do with my experiment. I replied that it fits the behavior of pencil lead written on the paper when there is a dramatic rise in the experiment. It could be the percolation threshold. The percolation model is due to the structure. The reason why we use the percolation model is due to the structure that we observe through the optical microscope. So we chose to use the percolation model. And so the opponent also asked, at the second experiment of IV curves, we seem to change the content of graphite, and why is F and 2H on the harder group? The reason why H is called H is because that they are harder pencils. So, and the reason why we separate them into two groups is because the magnitude of resistance is different. And so, third, how are we sure that the pencil line is an ohmic conductor? Well, we see in our experiment that we see that the IV curve of the pencils aren't linear. So we think that the conductor is not ohmic conductors. And so finally, the opponent asked how long is the pencil line, and we in our experiment we also see that the length and resistance are proportional. All right. So and the opponent asked the opponent also asked about the maximum downward pressure, but unfortunately we're unable to see the destruction of the graphite pencil because the paper is weaker than the pencil.
Okay, thank you. Any question, Joey?
Do you see the break direction breakdown to explain the nonlinear?
Yes.
So have you estimated the size of the dielectric and the breakdown voltage?
The breakdown voltage? Well, we breakdown voltage. Breakdown voltage. Well, we only we didn't have a really clear idea of the breakdown voltage of the relation between the size of the gap and the breakdown voltage. But well, I have to admit that we only have the qualitative description of the dielectric. I'm sure that we have observed the dielectric breakdown, but we have no idea. We have no clear idea about the exact breakdown voltage.
So I think based on this experiment, I have a question for all of you. So is it conclusive to say it's an ohmic material or a semiconductor?
Well, in my opinion, I wouldn't say that it is an ohmic because the IV curve is not linear. Again, I refer to it again. And I also, well, I didn't see the strict characteristics of semiconductor, so I wouldn't determine this to be a semiconductor. But what I want to say in this experiment is that when the voltage gets to beyond, when the voltage increases, we could observe that there is the current keep rising, and we could see that the conducting line has burned down. So there is an increase in the temperature of the conducting line too. So yeah, I have answered the question that it is not an ohmic conductor, and it is also not. I don't know if it is a semiconductor or not in this experiment. Right.
The opponent does not agree with what the reporter said. Since that the reporter has admitted himself that there are arrows that the line will burn out, so the experiment result is not correct. So the real relation between the voltage and the current may be different. And the reporter also measured the voltage only to 50, and it can also reach higher, and maybe it will have different relation between them in the larger scale of measurement.
I would like to correct what you said. I wouldn't say that burning out is the error of the experiment, because that is actually the phenomenon that we observe in this experiment. And because of the burning out, so we could say that there is a dielectric.
The opponent actually does not care about whether if the pencil burn out. The opponent only cares about when the temperature increase. According to the temperature coefficient, the resistance, which is the relation between V and I, will have a change.
Yes, of course.
Yes.
But it is not. It is
so
not
it will
designed.
cause error according to the temperature coefficient.
So thank you for the
Since they have a complete
said from our chemistry knowledge that the pure graphite isn't a semiconductor. And since they have right here, this is the pencil, and the material of pencil, it included the clay and the graphite. So this is actually a mixture. And so probably there are some some characteristic similar to the semiconductor, but we still can't assume that it is a semiconductor.
Okay, thank you. Okay. 7875888. Opponent 7976888.
Thank you.
Reviewer 7, 9. Okay. Thank you, everyone.
我相信你们3队应该会有人可能会去代表，因为我发现昨天到今天参加了2场哈，昨天选手的表现平平，今天你们3队都相当不错，所以我尤其是在 Stage 2的时候看到了3方面都表现得非常好哈。那我在这边给你们一些小小的建议。第一个，将来国际比赛的时候，他们的英文绝对比你们还溜了哈，所以你的听力还有口语的能力要加强哈。那另外，你们对物理知识的诠释哈，我觉得这都是你们很棒的一个地方哈。那也要诠释正确哈。那还有就是，尤其面对将来国际比赛的时候，会有对方挑战的这个部分。其实我觉得上一场 Stage 2的时候，我们几个评审有 challenge 你们哈，我觉得你们应对的都相当不错，所以都有加分。这三个角色了哈，所以其实你们就事论事，然后心理素质这一块，就是遇到这种挫折或抗压性的时候，不要紧张，不要紧张，紧张就容易失常，失常就容易讲错话，那这个时候就可能会被扣分，那另外在 Stage 2的时候，你们的时间控制都还不错。那在 Stage 1跟 Stage 3的时候，有的同学没有善用那个时间，问的时候没有问完， 那个也会被在国际比赛也会被扣分。我们怎么样要得到在国际比赛得到最好的成绩啊？就是把你的表达能力、抗压力，还有挫折容忍力啊这个部分啊，很快的调整一下啊，包括我们今天在这边的时候，器材临时有状况，你要去思考，如果将来在国际比赛的时候，不归咎于你的因素的时候，你怎么样随机应变的能力也是蛮重要的。所以我今天发现，昨天我们那一场初赛一没有用到的地方，你们今天三组都用到，就是用那个黑板，用黑板表达自己的观点。我相信国际比赛也许也会有那种现场会有白板笔啊，如果你可以做这样的一个沟通啊，或是一些表现的话啊，在 presentation 的时候善用一些媒体啊来做的话，相信你会表现得更加好。那很抱歉，我明天要到花莲女中的资优班演讲，所以我就没有办法看到你们的决赛。但是我相信你们3队一定会有人挺进决赛，或是相当不错的，祝福你们啊，祝福你们，谢谢，谢谢教授。
好，这个短短的间，其实你们应该都未来会一直往上爬。那我是建议你们有很多有做模拟的部分啊，因为你们做排程那种 V 排程的形式可以现象学，因为有些评审他不一定每个对这题目都很清楚，其实在现象的描述，你可以给评审更好的印象。好 ，OK， 好，谢谢各位。
好，谢谢教授。